So a couple warm-ups, just reminding ourselves how logarithms work and how exponential things work. So if I'm trying to solve log base 9 of log base 2 of x equal to 1/2, this is where it's kind of something that's important to see, and this definitely comes up in calculus later on, is when you have like a function of a function, kind of observing which function is the outermost function first. So when I see log base 9 of log base 2 of x, I'm seeing that log base 9 is like the outermost function. It's kind of the thing that's happening last. But when we write this, we're going to have to kind of see that first. So I see log base 9 of some stuff equal to 1/2, and I'm going to rewrite this as 9 to the 1/2 power equal to that stuff. The stuff being log base 2 of x. Oh, finish this up. Now, we could go on like this and just rewrite it as 2 to the 9 to the 1/2. But we should be a little bit more careful here. We know that we can simplify 9 to the 1/2. That's the same as the square root of 9. So we should definitely rewrite this as 3 equal to log base 2 of x. And now we've come across one of my favorite logarithmic equations where you've got log base 2 of something equals 3. So we're going to rewrite this as 2. And it doesn't really matter which side you write things on. I'm trying to go back and forth. You can write the 2 on the right, the 2 on the left. It doesn't matter as long as you're writing the right thing. So I'm going to say, well, I know I have 2 to the 3rd equals x. So I have 2 to the 3rd equals x. Okay, so I turned it up. All right, I turned on my email because a couple students had trouble getting into Zoom in class, and I was going to see if they email me, but I really got the sound on my email on, which is terrible. So I'm going to close that because it keeps doing things. So 2 to the 3rd equals x. So we've got 8 equals x. And I guess I should address, it's probably worth noting that we could plug back in 8. Log base 2 of 8 is 3, and then log base 9 of 3 would be 1/2. They give you valid, they're in the domain of the I will also mention, I did post a couple other examples of logarithmic equations on Canvas about how when you can have like a negative as your answer and not the positive thing. So you should look at those if you want to see a couple more examples. I think they're decent examples. All right, let's go ahead and look at the next thing. Also, if you guys are on Zoom, if you have any questions, don't hesitate to just write something in the chat, pipe up. So 10 to the 2x minus 3 equals 4. Normally, I would take the natural log of both sides because that's just my go-to. But here specifically, since the thing being raised to a power is 10, it would also be totally reasonable to use the log base 10 because that's the other kind of normal logarithm that comes up all the time. So I feel like you could either go in a natural log of 10 to the 2x minus 3 equals the natural log of 4 sort of direction, or you could go in a, you could just rewrite it, or you could actually take log base 10 to both sides and say log base 10 of 10 to the 2x minus 3 equals log base 10 of 4. Now I'm writing the base this time. I'm not going to write it in the next step, right? Log base 10, we don't write the base typically. On the left side, the 2x minus 3 comes down. So we have 2x minus 3 in parentheses times the natural log of 10 equal to the natural log of 4. On the right-hand side, same deal. The 2x minus 3 comes down. We've got a log base 10 of 10. Everybody should think about what that's equal to. Equal to the log. Oh, I said I wasn't going to write the base anymore. Oh, well, I lied. Sorry. I won't write it in the next step. Unless I forget, and then I will. Okay, so everybody on your fingers, not that finger. What's log base 10 to 10? 1 on your fingers. Yeah, sorry. So that's going to be just 1. So check this out. On the right-hand side, we can either do it this long way where you take the log base 10 of both sides, or in this next step, you can say, oh, look, I've really just got my power, 2x minus 3, is equal to log base 10 of the thing it's equal to. It's what you would get if you just went straight to rewriting it as a logarithmic equation. And I'm going to not write the base this time. So that's log base 10 of 4. We can write the base because it's base 10. And then we could solve for x here. I guess I'll finish this side first. So 2x equals log of 4 plus 3. And then finally divide both sides by 2 and get x equal to log of 4 plus 3, all divided by 2. On the other side of things, it's a little dicier. So I will point out, it is certainly nicer to use the base that you have. It just is. But that base isn't always available on a calculator, so we often default to natural log. Here, I would distribute the natural log of 10. Let's say I have 2x times natural log of 10 minus 3 times natural log of 10 equal to natural log of 4. I'm going to bring this over to the right-hand side, so I have all my x's on one side. So I have 2x natural log of 10 equal to, we're knocking on our door? No? Okay. Right, there's no one out there, right? No? We're good? Okay. I thought I heard someone knock. But I'm just old, sorry. Hearing things. So we have 2x natural log of 10 equal to natural log of 4 plus 3 natural log of 10. And then finally, we divide everything by 2 natural log of 10. So we're going to get x equal to the natural log of 4 plus 3 times the natural log of 10, all divided by 2 natural log of 10. And I think it's not too terrible here to see that both of these answers are pretty much the same. On the right-hand side, we have 3 over 2. I'm looking at that part first, the 3 over 2. On this side, we actually have the same thing. 3 natural log of 10 divided by 2 natural log of 10. The natural log of 10 would cancel and you would just get 3 over 2. And then the other part, here you have log base 10 of 4 over 2. You have the natural log of 4 over 2 natural log of 10, and those are the same thing if you use the change of base formula. So you really do get the same answer. Either way of finding it is fine. Usually we default to one of these two bases. But if I was solving something like 6 to the 2x minus 3 equals 4, I wouldn't use log base 6 because it's not a great option. I would use the natural log. That said, really, in general, if you're solving something like this and you're just writing out your answer and you're not like having to actually get a decimal approximation, using any base you want is fine. You can use the natural base, you can use log base 10, or you can use whatever the most convenient base is. So if it was 6 to the 2x minus 3 equals 4, it would be totally fine to use log base 6. Whatever makes the most sense to you. All right. Oh yeah, fun stuff. So these next ones I always think are interesting, but can be a little bit confusing. So look at all this given information. Given that log of 2 is approximately 0.3 and log base 10 of 3 is approximately 0.48 and log base 10 of 7, right? We have all these approximations. So you can't see what I'm saying here. You can see that on paper. Natural log of 2 is about 0.69 and so on and so on and so on. Approximate the following logarithms without a calculator. The whole point of this question really is to force you to use the properties of logarithms so that we can then evaluate these things. So in my whole list here, I don't have log base 10 of 21. Yes, I could totally just plug it into a calculator and get an answer. But the point is to not do that. The point is to test our ability to use the properties of logarithms. So I'm going to rewrite log of 21 as log of 3 times 7. Essentially, you're going to be looking for how to factor something or write it as a quotient or as something to a power. And then we're going to use the log properties to say, oh, that's going to be log of 3 plus log of 7. And again, that's log base 10 of 3, log base 10 of 7. And then we have each of those things in our list. We know that log base 10 of 3 is approximately 0.48. And log base 10 of 7 is approximately 0.85. And if we add those together, we get approximately, what, 1.33, I think? Yeah. And that's our answer. If you check on a calculator, it'll be close. It won't be exact, but it'll be close. You might be off, like, so I will point out that if you do use a calculator here, your approximation might be off by a little bit because like we've taken two approximations only to the 100th decimal place and add those together. Those might each be off by enough that your actual approximation might be like 1.34 something or 1.32 something. So don't worry too much about the fact that these are off by a little bit more than maybe you would normally be. All right. Natural log of 10. So what, let's see. So if I'm looking at my natural log, I have to see it. I have natural log of 2, natural log of 3, natural log of 5. And those are the, oh, and natural log of 7 down here. I didn't see that. So I need to think of things that get me to 10. Not by adding, right? We need to think of things that either multiply or divide to 10. Here, I'm going to think of natural log of 2 times 5, which is then going to be the natural log of 2 plus the natural log of 5. And then that's approximately 0.69 plus 1.61. And those add up to 2.30 approximately. Hopefully this next one is not too terrible. Log of 2 over 7. I think the division rule is the one that's screaming at us here. Right? If I have the log of 2 divided by 7, I'm going to write that as the log of 2 minus the log of 7. After this one, I'm going to throw an extra one in there. So let's see. Log of 2 is approximately, it's on my list here, 0.3. And the log of 7 is approximately 0.85. This is going to give us a negative number. It's going to be negative 0.55, which is okay. You can have logarithms. You can't take a log of a negative number, but you can have a log of a number equal to a negative thing. Let me throw another example at you though, because I feel like that one's maybe a little too easy. Let's try this. Here's an extra example. Let's try natural log. Yeah, natural log, that'll be fine. Natural log of 0.75. That seems like that number is not on my list. So the idea here is that if you were given a logarithm of the decimal and you're given all these other logarithms of not decimals, is to rewrite that decimal as a fraction. So how can we write 0.75 as a fraction? Right, exactly. So I've got the natural log of 3/4, and then I can break that up as the natural log of 3 minus the natural log of 4. I have one of those things. I have the natural log of 3. I don't have the natural log of 4 though. But I do have something that 4 is a power of. I have the natural log of 2, exactly. So the idea is if you see something you have to take the natural log of, and it's not a number you have, but it's a power of a number you have, you can say, oh, I'm going to write this as the natural log of 3 minus the natural log of 2 squared. And then that power of 2 can come down in front. And we're going to get that this is equal to the natural log of 3 minus 2 times the natural log of 2. And now all the things in my expression are on my list. I know that from my list, the natural log of 3 is approximately 1.10. And I know that, oh, sorry, not plus, minus, that's the worst. Terrible, James. You do a better job. Minus, biggest minus sign ever, okay. 2 times the natural log of 2, which is approximately 0.69. So then 2 times 0.69 is going to be, let's see, that's going to be 1.38. 1.10 minus 1.38 is about negative 0.28. So even if it doesn't look like the numbers you have are in there, they're in there somewhere. They just might be a little more hidden. Like in this next one, I think. This next one also, I think there's some hidden numbers. So I've got the natural log of the cube root of 4/15. And I'm going to first deal with that cube root and write it as a power instead. So I'm going to write this as the natural log of 4/15 to the 1/3 power. And then bring that power down. So we're going to get, this is 1/3 times the natural log. Now, I could write 4/15 again. I guess I will. But I feel like you could also totally skip this step and go straight to breaking it up as the first thing minus the second thing. So it's going to be 1/3 times. Now, I'm going to make a small mistake here, but we're going to fix it. The natural log of 4 minus the natural log of 15. And the small mistake there is 1/3 should be multiplied by everything here. But when I've written it this way, the 1/3 is only multiplying the natural log of 4, and it's not multiplying the negative natural log of 15. So what I really need here is brackets or parentheses to show that the 1/3 is still multiplying everything. And I don't think you could distribute it to each term, but you don't really need to. I would instead do all of this on the inside, and then at the very end, after I've gotten my inside approximation, multiply by 1/3. So now, same sort of thing as before. I don't have a natural log of 4, but I do have a natural log of 2. So I'm going to write this as the natural log of 2 squared. And the natural log of 15 is the natural log of 3 times 5. Okay, keep going. So let's see, we're going to bring down the 2. So we're going to have 2 times the natural log of 2, just like we had previously. And instead of the natural log of 3 times 5, I'm going to have the natural log of 3 plus the natural log of 5. Again, here comes a small error that we're going to fix. So if I write it like that, it says minus the natural log of 3 plus the natural log of 5. But really, I should have minus all of this. So I should really have minus parentheses the natural log of 3 plus the natural log of 5. Right? It's minus all of that. It's minus all of that. And then we're going to distribute the minus sign. So here's what we've got. And I'm going to start plugging in the approximation value. So I'm going to use an approximation symbol instead of like the actual equal sign. It's going to be approximately 1/3 times 2 times 0.69 minus the natural log of 3, which is approximately 1.10, minus the natural log of 5, which is approximately 1.61. Right, we are distributing that minus sign to each of those terms. Okay, I'm going to run out of room here. So this is going to be, sorry, I know it's terrible when it's going all over the place here. This is going to be approximately 1/3 times, you can see that, right? Yes. Let's see, that's 1.38 minus 1.1 minus 1.6 is minus 2.71. When we subtract those, we get 1/3 times negative 1.33, which is approximately negative 0.44. Yes, it's totally fine to use a calculator at the end here to do these additions or subtractions or divisions, because I know that's not super straightforward for everybody. But don't just use a calculator to figure out what the natural log of this is, right? Like, do this breakdown. The whole, so again, kind of back to why we are doing this. At least the reason I think why we're doing this is because eventually what you're going to see when you take either 16A or 16B or 17A or 17B or 21A or 21B, you're going to see that you're going to have to take the derivative of a natural log of something gross. And the point of this is going to be that, well, not the point, but the way we're going to make it not terrible is to first expand it out into lots of simpler logarithms and then take the derivative of it. So it's not terrible to do. So really, one of the reasons we are practicing this idea of expanding things using these rules is so that we're able to do it later when we need to differentiate things that look terrible. Yeah. Okay. That's most of what we have when it comes to logarithms. You can expand them, you can compress them, we can solve some logarithmic equations. That's, I mean, I should say, nothing in this class we are going to into all the details of, because there are millions and millions of little details about it. But that's pretty much how logarithms are coming, right? We've got kind of the rules, we've got how they work. We're going to move on. We're not completely done with them, but we're going to move on. Meaning they're going to pop back up, but in a slightly different context. So let's keep things in order here, James. Okay. Sorry, everything's out of order. Come on in, have a seat. So the other thing we're going to talk about today is simple interest, which it's interesting. I was actually looking up what the definition of simple interest is, and I think we in our department use a slightly different definition. So I don't think it's something to really worry about too much, but I will clarify as we go along. So simple interest is money you can earn by initially investing some principal, and then a percentage of that principal is as the principal making your initial investment grow. So like a bank account, right? You put money into it, they give you some piddly amount of interest back, and it eventually grows. So let's look at some examples. Say you invest $1,000 in a bank account that earns 5% interest every year. How much money will be in your account after 1 year? So even though it seems like a not too terrible question to answer, let's actually kind of write it out so we know what's going on. So the total that we're going to have after 1 year is the amount we started with, which is the principal, which is a word I always want to misspell, principal. Not principal like a student principal, like a principal, plus the interest we earn. Great. So in this case, the principal is the amount we invested, $1,000, plus how much did we earn? Well, we earned 5%. 5% of what? Of $1,000. So to calculate 5% of $1,000, we're going to multiply 5% times $1,000, but we're going to do it using the decimal, right? Instead of doing 5% times 1,000, we're going to do 5% as a decimal, which is 0.05 times $1,000. 0.05 times 1,000 is going to be, here's the way I always think about it. I know that 50% of 1,000 would be $500. So 5% is going to be a tenth of that, which is $50. So it's going to be $50. And that's going to add up to $1,050. Okay, so how much money will we have after 2 years? And this is where I will fully admit I'm probably actually using technically what is the wrong definition of simple interest. What I'm thinking of when I think of simple interest is every year you get another 5% on all the money you have, which is technically wrong. If you look up a definition of simple interest, what they'll tell you is you only get interest calculated on your principal every year. So for example, I could invest $1,000 and say how much simple interest are you going to earn over 10 years, and it would just be $50 each year. Because maybe you're taking the other $50 out. I don't know. It seems like not a great definition, personally. So I would also say, don't worry about it. No one's ever going to ask you about simple interest because it's not a very mathematical concept. So let's talk about what we really want to get at, which is eventually working towards what we're talking about next class, which is compound interest. But we're really going to talk about it right now too. So year 0, how much money do we have? Well, that's just when we invested the money. We have $1,000. Right? Today, I invested $1,000 at year 0. And then year 1, October 10th, 2023, which will be Tuesday. How much money do we have? Well, we know that we're going to have our $1,050. We're going to have our $1,050, which is just the $1,000 we started with, plus the $50 of interest. Which I will point out, and this is where things get kind of important, this is our principal of $1,000 times 1.05. 1 for the 100% of stuff we started with, 0.05 for the 5% of interest we earned. Now, here is where the calculation gets more interesting. How much money are we going to have after 2 years? So October 10th, 2023, we have $1,050. And now we're going to say that is all our money. We're going to leave it in the bank, right? The bank paid out our $50 of interest right on October 23rd, October 10th of next year. We're going to leave that $50 in the bank, and then we're going to ask, okay, after another year of earning 5% interest on that new total amount of $1,050, how much are we going to have after that? Well, let's see. We're going to take our $1,050 that we are quote unquote starting with, and we're going to add on 5% of that amount. Well, that's going to be 0.05 times $1,050. Now, here's the math I want you to see. You can really see it. I didn't say this when I was doing it over here, but I'm going to say it now. I didn't say it because no, I'm not going to say it. Sorry, my brain's like, no, that's actually not a good thing to say. Never mind. Apologies. What I'm going to say here is, what can you factor out from both of these terms, this 1,050 and this 0.05 times 1,050? And if I factor out 1,050, I'm left with a 1 here and a 0.05 here. But now look back. 1,050 is just 1,000 times 1.05. So what I really have here is $1,000 times 1.05 times another 1.05. Or, as I would prefer to write this, $1,000 times 1.05 squared, which I will tell you is approximately, or maybe exactly, I think it's exactly, sorry, $1,102.50. So after 2 years, we earned a little more than $100, right? We earned $50 the first year. And then the second year, we earned another $50 on the interest on the principal we had started with. But then we also earned 5% of the $50 interest we had earned. So we got 50 plus another 50 plus 5% of $50 is $2.50, which is all right there. $1,000 plus 50 is 1,100 plus another $2.50 is $1,102.50. So let me stop for a moment and ask you guys have any questions or want me to clarify anything I've said. Yeah. Well, what I would say, yeah, we're adding 5% of the previous amount. So like, so here what I did was, right from the beginning, I had $1,000 and I added 5% of that. I got $1,050. And then from this step to the next step, I had $1,050 and I added 5% of that. And 5% of $1,050 is $52.50. Right? Because it's 5% of 1,000 is $50. 5% of 1,050 is a little bit more than $50. It's 50-50. So let me ask you all now, if you had to guess how we would calculate how much money we had after 3 years, we could do all the math. We could say it's going to be this amount here, $11.0250, and we're going to take 5% of that and add it on. But what ends up happening is every time you go another year, you're just going to multiply by another factor of 1.05. One, because you have 100% of what you started with, and the 0.05 because you're earning another 5% of what you already have. So at year 3, we're going to have $1,000 that we started with in the very beginning times 1.05 to the third power, which I didn't actually write down what it was. I have to calculate it out. Here's what my guess is. I know I'm going to earn a little bit more than $50. It should be somewhere in the neighborhood of $1,152. It should be a little more. I think it's like $1,155. Let's see here. So let's see, we have 1,000 times 1.05 to the third power. We get 1157.62. You guys can barely see that, but it is $1,157.62.5. Yes, I know we don't get a half a cent, but we're going to write it down anyway. So every year we compound, every year we get 5% more interest, we're getting a little bit more interest, right? The first year we earned $50. The second year we earned $52.50. This year we earned like $55.12.5, and so on and so on. Every year earning just a little bit more. So again, I should maybe, I don't have the simple here. I'm going to cross that out because technically there's a different definition of what simple interest is. But we're going to say that annual interest is calculated this way. Every year, where T is the number of years. Wow, year starts with a Y, not an R. There is an R in there. So every year that you're earning some interest, this is how we're going to calculate it. Just to kind of label things here. A is the amount of money you're going to have after T years. P is the principal or the amount you're starting with. And R, now R is important. I mean, it's all important, but R is specifically important. R is the interest rate, but we have to write it as a decimal. Be careful. I see people lose the zero a lot on this. So if my interest rate is 7% as a decimal, it's going to be 0.07. If my interest rate is 70%, it's going to be 0.7. So make sure you move that decimal over 2 places when you're changing from a percent to a decimal. Most of the time, our interest rates are less than 10%, so there should be like a 0.0 something, but just be aware, right? You can have interesting things happen with them. Be careful. All right, let's look at a few examples here. Now, the reason we're talking about this really is to eventually lead us to the compound interest formula and to talk about my favorite number, E. That's not my favorite number. It's one of my favorite numbers, though, and a very important number. So let's look at some examples. Maria opens a savings account that pays 5%, again, 5% all annual interest. She puts $100 into the account. How much is in the account after 5 years? So we could do every year, but we know that using our interest formula, the amount of money equal to P times 1 plus R to the T. It's really just a throw all the numbers in the formula kind of question, which is what a lot of these questions are. They're kind of just toss it all into the formula and see what the answer is. And it does really kind of require a calculator. These questions you will need to use a calculator for to get an approximate. So let's see what we've got here. The amount of money after 5 years is going to be, and I would write it as A of 5 because it really is a function of time. My principal is $100. My interest rate is 0.05 as a decimal. And the number of years is also 5. And then, and maybe we can even write those things on the side, right? The principal is $100. The interest rate is 0.05 and time is 5 years. Then it's just use the calculator. So we're going to get, you could do, I would do one simplification first. I would write this as 100 times 1.05 to the 5th power. We can do that addition very, very easily in our head. But then I don't know what 1.05 to the 5th is. I have to use a calculator. So let's see. I wish I could make this easier to see. Can I make this brighter? No, that's worse. Not you can't see that even a little bit, can you? No, I can't see it. Okay. I'll just do it on my own here. 1.05 to the 5th. This is going to be approximately $100 times 1.2763. And then if we multiply that by 100, we're going to get approximately $127.63. Just to contrast that with what actual simple, so here's what actual simple interest would be. If I said we were actually getting simple interest on this $100 at 5% for 5 years, we would get $25. We'd get 5% every year on the original amount, no compounding happening. So that's what actual simple interest is, but it's not a very real world concept. And now here's what I say is always kind of the variety, the spice of these questions is that really with these types of questions, which are either interest questions or later on when we talk about exponential growth and decay questions, there's kind of only 2 things I can do. Or there's only kind of 2 questions I can ask you. I can ask you, how much money do I have after so many years? Or what year is it when I have so much money? I can either say I have this much time and what's the amount I get, or if I want this amount, how much time does it take? I can really only ask you one of those 2 things. How much time or how much money? Or how much time or how much stuff? So here we're asking the other question, right? Instead of saying you have 5 years and how much money do you get, I'm now asking how long does it take to get to $1,000? So now we know that our principal, right? It's still the same numbers. I don't really need to write down the same stuff again, but I'm going to because why not? We have the same deal here. But now instead of, right, we actually don't know what time is. Time is what we're trying to figure out. We do know that the amount should be $1,000. So the idea is we're going to substitute all of the things into our formula and solve for the one thing that is unknown. So here now I'm going to have $1,000. You also don't have to write the dollar symbol when you do this. Like I'm doing it to be specific here, but if you don't want to write the dollar symbol every time, don't. $1,000 equals $100 times 1.05 to the teeth power. Sounds like I'm saying teeth. Okay, so now we're going to solve for t. whenever you're solving an equation like this, where you have a variable in your exponents, there's two things you need to do. Thing one, the thing raised to a power needs to be isolated. To isolate 1.05 to the t power, we need to get rid of that coefficient. We're going to get rid of that coefficient by dividing both sides by. So I'm going to have $1,000 divided by $100 is equal to 1.05 to the t. And we'll point out $1,000 divided by $100 is 10, not dollars, just 10. Right? When you divide something by another thing with the same units, the units essentially cancel out. So we end up getting 10 equal to 1.05 to the t. And now the second thing we need to do is we're trying to solve an equation where the exponent is a variable. We typically take the log of both sides. You could use log base 10. I would probably use the natural log though, because my base is 1.05. So log base 10 doesn't make sense. You could use log base 1.05. I mean, you can, like it would be totally fine if you did, but I don't recommend it. I'm gonna take the natural log of both sides. I think I use log base 10 in my notes. Fine. I'm gonna use natural log over here though. Natural log of 10 equals the natural log of 1.05 to the t power. And the whole reason for doing that is to bring the power down. We want that variable not in the exponents. So then we have the natural log of 10 equal to t times the natural log of 1.05. And then finally, to solve for t, we're going to divide both sides by the natural log of 1.05. So we're going to get the natural log of 10 divided by the natural log of 1.05 equal to t. Now, although that is the correct answer, right? That's the actual right answer. It's not very meaningful, right? Like, I don't know how long that is. I don't know what natural log of 10 divided by natural log of 1.05. So even though this is the exact precise answer, typically when you're doing a question like this, you should actually use a calculator to get an approximation, because otherwise it doesn't, like, okay, how many years was your money in the bank for? So using a calculator, we get approximately 47.2 years. Which, I mean, doesn't seem unreasonable considering we're asking how long it takes for her money to multiply by 10 times, and it's earning 5% every year. It's going to take a while. Okay, so I would encourage you all that if you have a question like this, definitely do find the decimal approximation using a calculator, even though it might not have asked you to specifically do that. All right. Yeah, question.
Maturity converts out to like log base, log base 1.05.
You could, sure. You can totally, the other way you could do this if you wanted to, which would totally be fine, is to say, I've got this equation here, and I'm going to rewrite this as log base 1.05 of 10 equal to t. My question, though, is that if you want to actually find an approximation for this, how are we going to calculate that? Some calculators totally have a log base x of y button. Some do not. And so here's the thing that I have avoided saying, but I will say right now just because I might as well. There is this thing called the change of base formula. We're not going to cover right this moment, but I'll tell you, if you're ever trying to find log base b of x, you can rewrite this using any base you want, meaning you can say this is equal to the natural log of x over the natural log of b, or the log base 10 of x, log base 10 of b, or any base you want, log base a of x over log base a. So here you could rewrite this as my favorite base, natural log of 10 over natural log of 1.05, which is what our answer was. So that's typically the workaround. If you're going to use a kind of off atypical base, the way we usually, if we don't just have a fancy calculator to get us back to a base we can actually plug in, is to use this change of base formula. We'll talk about that later, though. Change of base formula, not a big deal, but it does come up sometimes. So yeah, you can totally write it like that. Fair point. Keeping things in order here. Okay. So let's see. That's the last one here. So most of the time, it's either how much time does it take to have so much money, or how much money you have after a certain amount of time. But this question is atypical in that they're going to ask you to find data. So let's see here. Suppose Billie Eilish puts $500,000 into a savings account, paying annual interest. Okay. After 2 years, there's $550,000 in the account. What was the interest rate? So again, we're just putting all the things into this one formula and then finding the thing that wasn't known. So we know that in fact, I want you all to write down the following. Write down what the principal was, what the amount after the time was, and what the time was. Fill in those things for me. I'll write down the formula. Okay, I'll do it too. As I've said a couple of times for these, a lot of these questions, most of these questions are really just like, for lack of a better term, plug and chug. Where you put the numbers into the formula, you find the one thing that's missing. Sometimes it's more work than others. This one's going to be a little more work than some of the other ones. So here, the principal is $500,000. The interest rate is the thing we don't know, so we're going to leave that as R. But we do know that the time is 2 years. And the amount after those 2 years is going to be $550,000. Sorry, I didn't mean to get that little, I'm trying to write something else there. Sorry. The one, way I fix all my mistakes is just to scribble over them until they look right. Okay. So what are we going to do first to solve for this? Divide, multiply, add, subtract. We're going to divide by that coefficient there. Even though there isn't a variable in the exponent, almost all the time, if you've got something multiplied by some other stuff, that coefficient there is a problem. So if we divide 550,000 by 500,000, we'll end up with 1 plus R squared. Now, 550,000 divided by 500,000, that is something we could simplify a lot. I don't want to write that again. A lot of those zeros cancel. I can reduce that to 55 over 50. I could even reduce that more, right? Because what still can I factor out from both 55 and 50? Right, so I can really reduce that to 11 over 10. Or if you prefer, 11 over 10 as a decimal is just 1.1. You don't have to change it to a decimal, but often if something's divided by 10 or 100 or 1,000 or some power of 10, it's really convenient to write it as a decimal. So I'm going to write this as 11 over 10 equal to 1 plus R squared, or really 1.1 equal to 1 plus R squared. Now, if I'm trying to solve for R, I'm going to take the square root of both sides. Now, a lot of the times when you take the square root of both sides, you get a plus or minus. Like if I was doing, or like if I was solving x squared equals 9, you get x equals plus or minus 3. But here, it wouldn't make sense for our thing to be negative, right? We don't, I mean, at least hopefully, we don't get negative interest rates, right? They're not paying you to take money, to borrow money, to use money, whatever. So I'm going to take the square root of both sides and say 1 plus R is equal to the square root of 1.1. And then I'm going to subtract 1. So that my interest rate is the square root of 1.1 minus 1. And that's my answer, but then I need to use a calculator to actually kind of figure out what that's going to be. So the square root of 1.1 is about 1.048. So this is approximately equal to 1.048 minus 1. I'm just writing it over here, which is approximately 0.048. So what's my interest rate? Right, about 5%. You can say about 4.8%. You can say about 5%. So about 5%, or if you prefer, 4.8%. Either one of those would be totally acceptable. Often this sort of idea of compounding interest, because that's really what we're doing, even though we're trying to avoid saying those words. I don't really have a good reason, but applies to loans as well. So when someone borrows an initial amount of money, the principal is the amount that's borrowed, and percentage of that principal, the interest, is added back to the principal, making the amount that is owed grow. Sometimes that amount is deferred, the interest is deferred, sometimes it's not. So suppose we borrow $20,000 in student loans this year, which seems like, unfortunately, not an unrealistic amount. You wait 10 years without making a payment, and the loans are not deferred. How much money will you owe the bank if you were charged 6% annual interest? So let's, again, the numbers really mean the same thing, right? Here, we're borrowing 20,000, so our principal is 20,000. The time is 10 years. The interest rate is what? It's 6%, but how am I going to write that as a decimal? Yeah. You don't always need that zero. Like I often don't write the zero in front, right? You don't have to write that zero before the decimal, although it's certainly fine to write it. I often don't though, because it's just lazy. But either way, just make sure it's definitely a 0.06 or a 0.06. So then we're just throwing this all into our formula, and we're going to get 20,000 times 1 plus 0.06 to the 10th power. And that would be our answer. And then if we use the calculator, it would be approximately $35,816.09. Compounding interest really does have a large effect as time